Okay, if my uh, poor and broken English won't let me down, I will try to tell you something about a small set of simulation I've performed a few weeks ago after some trouble happened on an exhaust system for a two-wheeler, for a two-wheel vehicle. I carried out the simulation using a model developed by a colleague of mine, and I will show you how this is me. Okay, a few words about Piaggio uh, for for those of you who never heard about it. Piaggio produces these things used in movies as well. Uh, Things that travel on roads on two wheels, but I won't show them. But Piaggio manufactures also small three and four wheel vehicles to carry things like tomatoes, potatoes, and so on. They're very common in Italy in the countryside. However, the most famous product is this called Vespa, and some others are these. This is the newest Vespa. You can get it with a two-stroke or four-stroke engines, even though the latter are much more common nowadays, especially for pollution issues. You can get engines from 50 to 350 cc displacement. And if you fancy some funny things and you are afraid of falling when you ride, you can get this kind of uh, let me say scooter. It has been very successful in Paris. I don't know why, but it has. Uh, this scooter can be equipped with an hybrid engine as well. The hybrid, because Piaggio not only manufactures vehicles, full vehicles, but it sells engines as well, standalone. And in this case, the Piaggio hybrid is mounted on this vehicle. Not only scooters from Piaggio, but also motorbikes, even in the racing world, uh, with some success. In 2013, the Aprilia brand won the championship as a manufacturer. And another rather famous brand is Moto Guzzi for long journeys on highways and so on. Is becoming to have some success in the US too. Okay, what has Piaggio to do with MSC? It's a rather long time user of some of MSC softwares, especially Adams. Mm, the first applications go back to the end of the last century for Piaggio. And I'll show you an application of Adams on a Vespa. The GTS is the biggest one, with engines ranging from 250 to 350 cc's displacement. In particular, I will spend a few words about the exhaust system, or more especially about the thing that supports the muffler. Uh, all the scooters that Piaggio makes share a common feature. The rear suspension includes the engine. If you look at this picture, you can see the engine cover is not very visible here, but there is a crankcase, and the whole engine vibrates. It's attached to one of the rear dampers, and so the engine is part of the rear suspension. If you look at the right-hand side of the vehicle, you can see the other damper, and here on the front part there's a mechanism which supports the engine, and the muffler is supported by this arm, which is connected to the rear wheel. In more detail, you see that this is here to have something strong that supports the weight of the muffler, and it is attached to the crankcase on the front side on these 2 points. There is an attachment point to one of the rear dampers, and finally, it is connected to the wheel axle here. So it supports the wheel as well. It's not the only support, of course, but it's one of them. So it has more than one function, but in this case, I will focus on its supporting function for the muffler. So, and this is the reason why this body is conventionally included in the exhaust system here in Piaggio. This is another Vespa. It's the newest one. Don't record this picture. Don't record this movie because it's strictly confidential. It's a new model. However, this is the durability test that more or less all our scooters have to undergo, and this test is used to assess the functionality of nearly all the mechanical systems of the scooter, the suspensions, the vehicle frame. And when I speak about suspension, again, I include the engine crankcase as well, because as you can see, the vibration are quite strong on this test bench. Okay, the problem in this case was that test was conducted without exhaust manifold. The engine is not turned on the bench, and this caused a problem. Or better, there was trouble, but we had to discover whether the lack of that pipe was the reason for the problem. What was the problem? The arm broke here. So again, durability test bench, no exhaust manifold, break. So the usual question: who was the culprit? Was it the missing manifold? How can I prove it? And especially, how can I prove it without having to perform another long durability test? Those tests last hundreds of hours. So doing them without being certain of the outcome, without a good confidence about the outcome, it can be a huge waste of time. So to avoid another physical test to investigate the cause of those failures, we resorted to simulation. And the main actor of those set of simulations was Adams. Uh, the job for Adams was to compute the loading condition. Of course, as you can understand, it's crucial to understand how uh, the body is loaded to assess its mechanical performance. I didn't have to build the model from scratch because, as you can imagine, being that an important test, a model was already available and it was used. It had been used to assess the vehicle frame functionality and some other suspension components. As you can see, this already available model lacks the all the exosystem because it wasn't needed at the time to perform those simulations. But no problem. Adams says it's by nature is modular, so you can add things, remove things very easily. This is another strong point of this software. There are two main ways of including things inside an MBS model, a multi-body model. A body can be described as rigid or flexible. As you describe it as rigid, you first of all you save time because the equation the solver has to solve are fewer and simpler. But and you use the rigid representation when there is no risk of exciting, for instance, natural frequencies, natural modes, shapes, and so on. So when the excitations are far below the natural frequencies, there is no reason why you have to resort to a flexible body. But there is another case when you cannot do without it, and this is one. When you have redundant constraints and a hyperstatic constraint scheme just like this, because here you have two fixed constraints, if you simulate this thing as a rigid body, you are not sure of getting all the load channels because Adams performs a redundant constraint check and arbitrarily removes the unnecessary constraints. So you run the risk of losing information. For this reason, you have to resort to a flexible body simulation here. And the info you need for to simulate that body as a flexible one comes from an FEM1. So this is the final model you can see here. Sorry, what I added. This is the famous, the notorious exhaust manifold. I can switch it off and on as I wish in Adams. This is the muffler. It's transparent to let you see what lies behind, and this is the main object of the simulation. Okay, so first, the multi-body simulation was split into steps. The first one is static equilibrium simulation. Static solver is invoked. These two big boxes here that you didn't see in the real movie are in fact used during the simulation to assess, to take into account the weight of the rider and of the passenger. Of course, it's truly important to set the dampers on their proper working condition. So this is a preloading, which affects, of course, the stiffness of the rear dampers and the front one. So once the static equilibrium condition was established, a dynamic simulation was performed. This is slightly different from the movie. In in the previous movie, there was an obstacle on the front wheel, but here there are two. This is the test the vehicle was being subject to when the failure occurred. The simulation time is quite long because you have to reach more or less a stationary condition in order to be able to perform afterwards a durability calculation. Okay, this is only part of the scene because Adams was not the only software used to get the desired result, but as I mentioned before, it was probably the main actor, and the the Adams the job uh, that Adams performed was crucial. Okay, so this is a flow. You start from the CAD model, and you get from that all the geometry information you need for the system. Its topology. The topology is a set of relationships between neighboring bodies, how they are connected. Uh, you have to know whether what kind of kinematic constraints uh, they share, and so on. And of course, all the inertial properties which are necessary to perform the dynamic analysis in atoms. The geometry is used in the FEM environment to compute the information you need to simulate the body as a flexible one inside atoms. The information are of of a model kind. So you perform in the FEM environment, you perform a set of calculations strictly related to the model content of the body. I will spend a few words about that in a minute. So, what do you put inside atoms? The geometry, all the inertia, all the the connections between the bodies, and all the information you need for that special body you have to analyze in terms of distributed flexibility, uh, again, in terms of its model content. After having provided Adams with all these things, Adams gives you this kind of information. That is, the model coordinate time histories. I will spend a few words about that in a minute. These, the model coordinate time histories, that are a sort of uh, loading condition, and the stress shapes which are peculiar of the particular body put together are the ingredients to compute in a durability package the fatigue safety factor. This is the number that tells you if a body is uh, due to break or not. So let's have a look at uh, the information you need to compute the stress time history of the flexible body. You have your MBS simulation, and Adams calculates for you these kind of graphs. These are the model coordinates, so-called model coordinates, and are peculiar of these bodies. You couple them with the stress shapes that comes from an FEM analysis. How you get these stress shapes. So with in this particular case, you have a value of stress at each and every point of the body. And if you multiply this stress distribution for this time information, you get a stress time history. But this is the contribution only of the first mode. So first natural mode of this body causes a stress time history obtained by multiplying its stress shapes by the model coordinate time history. If you repeat this procedure, so you multiply the stress shape by the time history of the model coordinates for all the modes, and you add them all together, at the end of the day, you get the overall stress time history in this body. It's a linear combination. When you have the time history of the stress, you have everything you need to perform a durability computation. So in this case, the first thing we did was to try to replicate the physical evidence. So the first simulation that was carried out was the one referring to the bench test without the exhaust manifold. From that simulation, I got the safety factor distribution with the CA flow-up just shown you. And I compared the safety factor distribution with the physical evidence. If the things match, my model is good. Having proven that the model is able to replicate the reality, then I asked the question that was posed to me, that was, if I include exhaust manifold, will I avoid the trouble? And even more important, since we wanted to adopt a new sport arm, a lighter one, how can I be confident that that new arm won't break on the bench test? Again, the answer was, I simulated and I will tell you if it is good or not. Of course, the relevant quantity is again the safety factor, the durability safety factor. In this way, you can be confident that the design is flawless, and so you can approach the bench test again with much more confidence, with a lower risk of wasting your time. Okay, let's have a look at this comparison. You can see here the safety factor distribution, the durability safety factor distribution coming from the simulation of the real test, that is the one without the exhaust manifold. As you can see, the minimum value is lower than 1. That means failure. If you compare this distribution, and in particular the location of the absolute minimum of this distribution, you see that it matches the position that was shown in the lab. That means that Adams did a very, very good job. The loading condition was truly accurate, because this is the only way you can get this very good matching between numerical values and experimental evidence. So the model was good. It was able to simulate the reality. Then you can use it to predict what will happen when you perform again the test, but with the exhaust manifold, and most importantly, if you try to test the new design. This is the outcome of these last simulations. This is the old arm, the old support arm simulated with exhaust manifold. The safety factor is truly high. So the culprit was the missing exhaust manifold. The suspect was correct. The suspicion was correct. Sorry. And if you switch from this arm to a new one, the lighter one, you lose something in terms of safety factor, but your value is still very, very high. You can be confident that these won't break on the durability test bench. Indeed, that happens. So there is no problem showed up during the subsequent physical tests. So a brief recap. The investigation of a few failures on a durability test was carried out by Adams, and that allowed to avoid further physical tests with a huge waste of time and possible waste of physical prototypes as well. Adams shown it was shown to be very prone to be easily modified by simply adding things to the existing model. And Adams proved to be very, very easy to couple with other software tools. It has all the interface features needed to couple it with whatever you want, more or less, in the CAE landscape. And most of all, it proved very robust and accurate. You have to think that that simulation is not so simple, even though the mechanical system is not incredibly complex, but the events are a succession of impacts with a flexible body included, with lots of nonlinear elements such as the spring dampers. So once again, Adams showed us a remarkable robustness and accuracy. And at the end of the day, that allowed to avoid a number of physical tests, and the test bench was again approached only when higher confidence of getting a good result was already available from the CAE simulations. So thank you very much.